So, hello everybody and welcome to this Thursdays at BrIAS seminar. I don't know, I lost the count, so more or less we are six. They tell me from the back of the room that it's our sixth session of seminars. And I am particularly happy to introduce the next speaker that, as you can see, forgot to put his name on his first slide. Yeah. So it's really a pleasure for me to introduce Marco Nicotra. So Marco is a professor at Colorado Boulder, and I'm particularly happy to introduce him because he was the first person who had the misfortune to start a PhD and finish it with me. So this a few years ago, unfortunately time passes. Among the most notable things, okay, this is an inside joke for the members of my research group. He was the first one that imposed in our group the tradition of the wooden sword. So, you know, so in our group we have this weird tradition that we give a wooden sword to whoever finishes his PhD. I could say, if we were in Star Wars, that I'm your father, academically speaking. But beside that, so Marco is very active in the field of constraint control, and in particular his main merit was to look at constraint control, but from a nonlinear control perspective, rather than the usual MPC perspective. Actually, what he told me when he was a PhD student, he was saying, I don't want to learn optimization, and so it's the reason why we went in that direction. And since there is a nice counterpoint to whatever you do in life, he did his postdoc in optimization. So I will not go on. I have a lot of stories that are more or less embarrassing concerning Marco, but they told me that this is not the stage to embarrass him too much. A little bit, it's fine. So I leave him the stage, and let's see what he is going to present to us today.
Thank you, Emanuele. I was wondering what to present here at BrIAS, and I was thinking about my most recent work on controlled barrier functions, which hopefully is sufficiently new. That is something that people can learn about, but also goes back to our roots on explicit reference governors. So just to give a general overview, autonomous systems are becoming more and more ubiquitous. We are talking about self-driving cars, smart grid, basically all these systems that are trying to improve our lives, and they are getting more and more automated and more autonomous. There's a huge industry around it, but the truth of the matter is that the computer doesn't work. Hello? We have a break. You can notice the nice pictures while the computer thinks about its next steps. In my defense, it's not my computer. Microsoft PowerPoint is not responding. Restart. No, cancel.
Okay.
Cancel.
Open it again.
All right. Microsoft respects my privacy, but not my presentation. All right, done. All right. Oh, yeah, we got to the third slides. So autonomous systems have a lot of, there's a great perspective on them, but we're still facing challenges, and these systems are becoming more and more complex, while also having stricter and stricter requirements in terms of performance. They need to be safe, reliable, flexible, but we also want them to be as small as possible and as cheap as possible. And so what's happening right now is that the old control design method of linearize the system, make it work far away from any nonlinearities, and just go with it, doesn't work anymore. So we are trying to design control laws that push the systems to their operating limits while making sure that they remain safe. And well, I'd say the gold standard for constraint control laws is model predictive control. At every time step, the model predictive controller looks ahead into the future and tries to find the best strategy for achieving its objective without violating constraints. It has a high computational cost, and it's also the one thing I promised I wouldn't do here. So even though I've worked on it during my postdoc, I thought I'm not coming back and talking about MPC. So an alternative method to MPC are what are called safety filters. And safety filters are just going to be a broad family of constraint control laws where you keep an existing controller, so there's no need to go and redesign the system. A lot of industries have had their control law for years. They've tuned it to what they consider perfection, and they don't want to give it up. So the nice thing about safety filters is that they allow them to keep those control laws, and they tend to have a much lower computational cost compared to model predictive control because they don't need to solve a full nonlinear control problem. And so I'm going to talk about a few different families of safety filters. The general idea is that first you design the control law for the unconstrained system, so you ignore constraints, design your controller, and then you introduce an add-on unit that enforces constraints a posteriori. And different kinds of safety filters will depend on where you place it. So control barrier functions are going to be a safety filter that is placed between your controller and your system. And so it filters the control input that goes to the system itself. Whereas reference governors is instead a safety filter that is put on the reference of your control law. So in one case, you filter the reference and you allow your nominal controller to do its job. In the other case, you interrupt what the nominal controller is doing and modify the control law. So I'll briefly go through sort of general idea of both control barrier functions and reference governors. And then I will show how to mix the two to develop control barrier functions. Brief history on control barrier functions. They're actually relatively recent in terms of control schemes and control literature. The oldest paper that talks about control barrier functions in what is their modern conception is from 2014. But really the literature exploded around 2019. So we were talking about 5 years of control barrier functions being used and being researched on. And so what are they all about? Well, we consider a affine continuous system. So the input enters your system linearly for a fixed x. And then we have state and input constraints, mathcal x, mathcal u. And our objective is to control the system while making sure that these constraints are satisfied. And then there's a definition of a control barrier function that's just about as useful as the definition of a Lyapunov function. So continuously differentiable function h is a control barrier function if it satisfies two properties. First of all, if h of x is positive, then my state needs to be inside the constraints. Doesn't say anything about h being negative, violating constraint, that doesn't matter. But the point is, if it's greater or equal than 0, your constraints are satisfied. And then the other requirement for control barrier functions is this. If h is positive, there exists a control admissible u that satisfies a long and ugly equation. So let's see what that means. You have this nabla h. This is the gradient of your control barrier function. Let's put ourselves on the boundary of where h is equal to 0. Then the gradient is nothing else but the direction that points into my 0 level set. Okay? And so the second part of this is nothing more than x dot. So we're basically saying that the inner product between the direction in which h increases, so the direction where I go into my constraints, needs to be positive if h is 0. And so here we have two cases. There's an x dot that points outside, and that's not allowed. There's an x dot that points inside, and that is perfectly allowed. All right? And then the question is, okay, why do we need this a of h? Why do we need this alpha of h on the right? Well, if we didn't have alpha of h, we could set this as sort of a subtangentiality condition, where you only care about what happens on the border, and then inside you say, okay, do whatever you want. What this term is doing is sort of smoothing the requirement. It's saying if you are close to being on the border, then you want to decrease at maximum with a certain amount. So it's basically saying as you get closer to the border of your constraints, slow down. And then when you get on the constraints, the requirement is you cannot decrease anymore. You have to increase. All right? And as I said, this is a very general definition of h of x. And it says if you satisfy these conditions, you have a control barrier function. And what do we do with this control barrier function? We design what is called a CBF safety filter that basically at each time step solves this optimization problem. So we have a nominal control input, un. That nominal control input could cause our system to go outside our constraints. And then we say we're going to design an input u that is as close as possible to what the controller is trying to do while still satisfying this requirement on safety. All right? And at every, well, this is in continuous time, so we continuously solve this optimization problem, and we are guaranteed to be inside the constraints. So once again, if h of s is a CBF and the initial conditions and its initial value is positive, then this optimization problem is always feasible. So it starts feasible, will always remain feasible in the future. And our control law ensures that constraints are satisfied. All right? So this is the general pitch behind control barrier functions. And the truth is that they work pretty well, and they've been adapted for robotics quite a bit. And so I'm going to go over a few examples of how control barrier functions work, how they can be implemented, and then what the pitfalls are. And here we're going to have a simple obstacle avoidance problem. We're on a plane. X and u are both two-dimensional vectors, so we can move this point mass in whatever direction we want. And we want to reach our reference, which is on the other side of the obstacle, while staying outside of a circular obstacle. And so first steps, we're going to design a nominal controller, proportional gain times r minus x, and this control law would normally just go on the straight line between your initial condition and the reference. Then, biggest issue with control barrier functions is that we need to find a control barrier function for the system. And this is where people have problems because there's no systematic way of generating control barrier functions. And so typically people just propose candidate CBFs and sort of hope for the best that the properties are satisfied. And in this case, we can take a CBF, the distance between my current state and the constraints. Here, this is basically the constraint. So x transpose x minus 1, if that's equal to 0, it means that the norm of x is 1. And that if that is positive, it means that we're satisfying the constraints. So in a way, we take the constraint itself and say, I'm going to use that as a control barrier function. And in this case, it does satisfy the properties. You can prove it. But in general, it might not. And then the CBF filter looks nothing more than this. It's minimize the error between your control input and the nominal control input subject to, this is the derivative of the CBF greater or equal than the value of the CBF times some scalar alpha. And you solve this optimization problem, and you get a trajectory that goes around the obstacle and to the reference. So I will say that the one thing that CBF, and I think the reason why CBFs have become so popular is the fact that they are extremely intuitive and very easy to implement. So you have a CBF, you propose these things, you have an optimization problem where the dimension is just the size of the dimensions of your input, as opposed to MPC, which also has dimension of your state, dimension of your prediction horizon, etc. So this is a very light optimization problem, very simple to solve online, and then you can get very good results without doing too much. All right, and slightly more interesting problem. I did so these are two carts connected by a spring. You can do the same exact thing with an overhead crane. It's just a bit more annoying to get all the other parameters, so I'll keep it simple. But for those of you who are fans of overhead cranes, we have everything for that too. But basically, we have these two carts of two different masses. They're connected by a spring, and the control input acts on the first cart. And we're going to have a constraint on the second cart. Okay? And then, and we have also a maximum input saturation constraint as well. And now we go through the various steps of designing a CBF. We choose a nominal controller, which is a PD controller on the first cart. And if we implement that controller without changing anything, this is the behavior that our system will do. I'm only plotting x2. You see that x2 goes over the constraint. And then the control input also has input saturation here and here. So the nominal controller was designed without taking into account constraints, and so it shouldn't be surprising that it violates them. And then once again, we need a CBF. And as a candidate CBF, we're just going to take 3 minus x2 because I want x2 to be smaller than 3. And once again, I'll stress this is a candidate CBF. It means that it satisfies the first property. If it's positive, constraints are satisfied, might not satisfy the second property. One thing I'll note is that when we go and compute the derivative of h, it's minus x2 dot, which doesn't depend on the control input. So already we've seen that if the affine system doesn't have a way for the control input to act on the system, then we're already in trouble. We can't use the CBF. Not to fear, this problem has been solved. And so there's the exponential CBF approach, where basically you compute the derivative of your CBF until the control input comes in. If you think about it, this is a fourth order system where the control input influences the acceleration of this mass, and then the position of this mass influences the acceleration of the second mass. And so this is, you need to, there's a relative degree 4 before you see the control input acting on your system. And so there's a slightly more complicated formulation for control barrier function that takes into account relative degree. And if you implement the CBF there, you get a control law that filters out what the control input should have been. And we get something that satisfies our input constraints and also satisfies our position constraints. All right? Great story. And I would say this is the reason why everybody goes to CBFs, is that it is very simple to implement. Unfortunately, we have no guarantees that, well, the candidate CBF we chose is actually a CBF. And in particular, what happens is that for different initial conditions, we might have constraint violation. So for example, for initial conditions that are at minus 13, we see that the carts go towards the constraints, and then you see the control input goes from an upper saturation, getting close to the constraints, you need to decelerate quickly, and you have a lower bound on your control input. And so what happens here is that the CBF has put itself in a condition where it can't decelerate fast enough to violate the constraints. So it either violates your position constraint or violates the control input constraint. It can't satisfy both, and it just fails. All right? Yes, with tuning, you can get it to work on this particular example, but then you can take another initial condition and violate it anyways. So the point is, sure, it works, and if you are in a sort of confined space, you can tune it in a way that everything works. But we want something that's a bit more systematic than just taking distance to constraint and tuning things until they work. Which brings us back to a different literature, which is reference governors. Reference governors, Manuel might correct me on this, but I think first time they were formulated 1995, slightly earlier for invariant sets, but this is the first time I saw the word reference governor. In any case, 30 plus years of history, and there is proven stability and safety results for it. And then there is this paper for 2015 that you might recognize the authors of. This is the paper that, this is the work that I did while I was a PhD student here. And basically, we formulated the reference governor for continuous time systems, and we use kind of nonlinear systems theory to enforce constraints. So I'm going to go a little bit into the theory of explicit reference governors because it's going to be needed afterwards. Kind of the same setting. We have x dot equals of fu, not necessarily affine, but this is more general. Again, we have stated input constraints. And for this particular system, we are going to parameterize the equilibrium manifold. So we assume that this system has multiple possible equilibrium points, and those equilibrium points can be parameterized by this variable v. And so x bar of v is a possible equilibrium point for the system. And, well, if we have a possible equilibrium point, we can design a control law that brings our system from x to an equilibrium point, and we call that a pre-stabilizing control law. So we start from a state x, and the pre-stabilizing controller leads me to my target equilibrium point. The nice thing is that if we have input constraints, those input constraints can be translated into state constraints, because now we have a pre-stabilizing controller, so we have a mapping that goes from state to input, and that allows us to reformulate our input constraints as state constraints. And then how do we know whether the trajectory is going to violate constraints? Because right now we're not enforcing anything. Well, we can always say that the trajectory is contained inside the level sets of a Lyapunov function. Okay? So here I don't care necessarily what the trajectory will do. I just note that there's a Lyapunov function associated to my current state. And there is a Lyapunov level set that is going to touch my constraint. So if you think about it this way, gamma of v is a distance between my reference and the boundary of my constraints, but sort of in using the Lyapunov function as a norm. So we're saying, okay, well, for this given reference v, what is the largest Lyapunov level set that I can have that doesn't go outside of the constraints? And well, it's fairly clear that if the value of the Lyapunov function is smaller than the Lyapunov threshold value, then you cannot violate constraints, because the Lyapunov function is destined to decrease, gamma stays the same, and so this value is going to decrease as long as V remains constant. And so that brings us to what the ERG looks like. The ERG, we manipulate this auxiliary reference V because that might not be the equilibrium that we want to go to. And so what we do is that we say, okay, V dot is going to be proportional to this error. So when the Lyapunov function is equal to the threshold value, we stop and we wait for the Lyapunov function to decrease. When it's strictly positive, it means that it's safe for my reference to move. And then this rho is nothing more than the direction in which I want my reference to move. It can move. Where should it go? Well, ideally, we have an actual reference that we want to go to. And so rho is just a vector that points from my current virtual reference to my actual target. And we can show that by simply manipulating the derivative of this fake reference, we can get a control law that guarantees safety and asymptotic stability. So what does this look like for our example? Well, once again, nominal controller, PD control law on the position of the first cart. And what is the Lyapunov function for this? Well, it is the total energy of the two-cart system where we also assume that this Kp is a virtual spring. And so the Lyapunov function is going to be kinetic energy of the first cart, kinetic energy of the second cart, a spring that connects the two carts together, and then this virtual spring that connects x1 to my reference V. All right? So I know that if V stays constant, this function is time decreasing. Now I need to express my constraints as constraints on the Lyapunov function, not constraints on the state. I'll skip over this. The first one is our input constraint. Your control law is a linear constraint. Your Lyapunov function is an ellipsoid. You can calculate the intersection between an ellipsoid and a planar constraint, and this is the result for it. It's not too exciting, but the solution is there, and you can calculate it closed form. Little bit more interesting is the second constraint. This is the constraint associated to I want x2 to be smaller than 3. And so what happens here is that I have a system where I have a reference V and a virtual spring Kp that connects the reference V to the mass 1. And then I have a real spring that connects mass 1 to mass 2. And so mass 2 sees a series of two springs that connects it to V. And you can compute the series spring constant, which is the same formula as parallel resistances. So this is basically the spring constant of a spring that connects x2 to x1. And now all we have is how far is my constraint of x2 from V. And so this is the minimum energy that I need to violate my constraint. And so if we implement the explicit reference governor on this system, we get something that looks like this. So here we notice that the candidate CBF and the ERG have more or less the same response, which is generally not true. But we see here the reference of the ERG, which grows, and then it kind of steadily goes towards your actual reference until it settles down. And so this is the same control law that generated this red line, but instead of giving it a step function, I gave it this time-varying reference. And just by changing the reference dynamics, we were able to enforce constraints. This is true for the case where the CBF worked. And actually here we can guarantee that it's going to be true for any initial conditions. So when we start further away, the reference governor is still going to safely take us to the target. Fairly obviously, though, it's doing quite a slow job at it. And that's the one thing that reference governors have against them, is that their main way of working is to slow down a system. So reference governors say, I can satisfy any constraint as long as I slow down your dynamics enough. And so it is sort of prone to having to have these slow responses. But at least it's safe, and it does asymptotically tend to the target. So it does satisfy things. But the idea here is like, okay, well, we have CBFs that have been shown to achieve fairly good performance when they work, but don't have guarantees that they will work. And then we have the ERG, which has guarantees that will guarantee safety, but the performance tend to be hit or miss. And so I can finally get what the main focus of this talk is, which is how do we combine reference governors and CBFs so that we can design a CBF that is guaranteed to enforce constraints. And so the results I'm presenting is from a paper that has been submitted to TAC. And if you're a reviewer, please accept it. Yeah, so just wanted to give you a little sneak peek at this result that I'm very excited about. So going back to the context, we need to take the most restrictive of the two between CBFs and ERG. So we're back to that affine dynamics. It's not a general f of xu, it's just f of x plus gx of u. And actually the main reason for this is to guarantee that it's the solution of your optimization problem is Lipschitz continuous. And so since we've done our homework on the reference governor side, we know that we can define this dynamic safety margin, which is nothing more than the threshold value for a given reference v minus the current value of the Lyapunov function for that particular reference v. And what we are going to do is we're going to extend the system. So rather than studying just the dynamics of x dot, we're going to study the dynamics of my system and this virtual reference. The system satisfies my normal dynamics. The virtual reference, its derivative is equal to rho because I get to choose the derivative to be however I want. And what we're going to do is apply the CBF optimization problem to this extended system, which is state and virtual input. And so the optimization problem looks something like this. You need now a nominal direction for your reference to go, but that's not too hard to get. And so we are solving over u and rho, and we're trying to minimize the error between our control input and the nominal control input, as before, and then possibly the error between the direction in which our applied reference goes and a nominal direction. This epsilon can technically be 0, but when it's 0, the problem's not strongly convex. So we do like to keep it small but non-zero. But the theory works even if this is 0. Rest of the constraints, the control input needs to be inside my input constraints. And then this is nothing more than what we had before. So sort of the gradient of delta times x dot plus the gradient with respect to v times v dot. And that's greater or equal than alpha times delta. So what we're doing is that we are using this dynamic safety margin as a control barrier function for a system that has extra states in the form of this applied reference. And the nice thing is that this particular optimization problem always has a feasible solution. That solution is don't do anything with the reference, so keep the reference still, and then apply the pre-stabilizing controller to your system. If that happens, your x will follow that predetermined trajectory, which means v will decrease, which means everything will work. Nice thing here, we don't care about relative degree of our system. Basically, if for any point we have one of these go to 0, we can actually prove that the natural dynamics of our closed loop system work. Okay, so that's the optimization problem. Going back to our favorite example, same Lyapunov function, same threshold value. The point of this is to say that everything that we've learned how to do on explicit reference governors can be ported into the CBF literature with no changes. And then once we apply the CBF, we get something like this. And so here, the measure of performance of a CBF, due to how the optimization problem is formulated, is how closely it follows the nominal trajectory. And so you can see that the dynamic safety margin-based CBF follows the nominal trajectory pretty closely, and then also stabilizes and doesn't violate constraints. The interesting thing to look at here is this applied reference, which isn't applied to anything. It's just a backup reference for our control law. The controller knows at this time that if it were to give a reference that's very far away from the constraints, then it's safe. And so it keeps in its pocket this knowledge of the fact that, oh, I am safe now because at any given time I can give a reference that's way back there, and by doing that I'm going to satisfy my constraints. And then we apply it to the longer step, and we get something that looks like this. It's actually doing almost exactly what the candidate CBF wanted to do. So input is fully saturated at the beginning, and the interesting part is that it saturates a little bit longer after. And then it does this because it knows that it can give a reference that's behind it at any given time to satisfy the constraints. And so what happens here is that it is able to then switch down, and now the control input doesn't have to saturate in order to get constraint satisfaction on X. So it's able to satisfy both your constraints on X and your input saturation constraints directly. Brief overlook of what we've seen. We're proposing a method to design CBFs in a systematic manner. The steps for this is you take your system and first you define a pre-stabilizing controller that stabilizes it to a generic reference, any steady state admissible equilibrium point. It's interesting to note, and we've actually used this quite a lot, that the pre-stabilizing control law doesn't need to be the same as the nominal controller that we use, that we then optimize against. In fact, we've seen that the best performance is obtained by having a very aggressive nominal controller, but a very, very slow and relaxed pre-stabilizing controller. Once you've defined the pre-stabilizing controller, you need to find the Lyapunov function for the pre-stabilized system. And you need to translate every constraint into a constraint on the Lyapunov function. And then we've proven that the difference between the threshold value and the Lyapunov function is a control barrier function. Properties that we've been able to prove. The optimization problem is persistently feasible. The relative degree doesn't matter, which is nice for people who have worked in control barrier functions, because most of the literature assumes relative degree 1, and then you need to go into exponential CBFs for anything higher than that. Here we're saying doesn't matter, it works, but it's because basically this gamma minus v will always have a relative degree 1. And then it satisfies constraint sharing properties. So far, I've only talked about having one constraint, but if you have multiple constraints, your optimization problem becomes more complicated, and it becomes more likely that the solution doesn't exist. And so for CBS, we can prove that as long as you use the same pre-stabilizing controller to compute all your dynamic safety margins, then you have the constraint sharing property, and you can add constraints without any worries. I do have time, I think. Do I? Yeah. So I'll go into another example where I wanted to say that the fault for the constraint violation wasn't the fact that the relative degree was so high. So I have a system where relative degree 1, you technically have enough control authority to get everything to work, and CBFs can still fail if they're poorly designed. So I have this nonlinear system that is, the first order terms are asymptotically stable, but then I have an unstable cubic term here. So what this means is that if I stay close to the origin, the system tends to come back. And then if I get far away enough from the origin, the cubic terms will overpower the linear terms and the system goes unstable. And here we want to reach r equals to 1.5 while satisfying constraints on x and input constraints on u. Chosen weirdly because that helps me solve the cubic plot, but doesn't really matter. We define a nominal controller. Here we're doing what in robotics would be called an end gravity compensation. So we're just computing what our steady state would be and enforcing a control input that is a constant plus something that multiplies my error. And with this controller, we get something like this. So we go from 0.5 to 1.5 without any overshoot. So the x constraint is not even a question. And our control input definitely violates our saturation constraints. And CBF filter, we're going to use our constraint as a control candidate CBF. And the system looks like this. So what happens is that it tries to go towards its target. And at a certain point, when the control input saturates, well, unfortunately, the cubic term is overpowering both the linear term and the saturated input. And so the system goes unstable. And so the interesting part here is that it doesn't really matter what my x constraint is. As long as I have a constraint, it will be violated. If I had a constraint x equals smaller than 200, it would also be violated. Basically, we've excited an instability of the system, and now whatever our constraint is, we can't satisfy it. And we can implement an explicit reference governor, usual things, pre-stabilizing controller. This is why I call it the anthill system, because the Lyapunov function looks like an anthill. And so you see you have two peaks, and basically if you're on the outside of these peaks, you become unstable. If you're on the inside of these peaks, your control is asymptotically stable. And so we have a natural constraint on our pre-stabilizing system, which is that we want the Lyapunov function to be less than the value at that peak. And if we enforce that, we guarantee that our control law, our pre-stabilizing controller is always stable. And then if we have other constraints, for example, I want x to be greater or equal than 0, then we can take the value of the Lyapunov function at that point, and we get a threshold value. So we translate everything into constraints. I'll skip over. But basically, the idea is that this is what the ERG comes out to be, and we can compute the threshold value in closed form. And once again, we are safe, but we might be slow. And then we use the same exact dynamic safety margin for our CBF, and we get something that looks like this. So it follows our target dynamics exactly until it realizes that there's a lower bound on U. I can't go any further, and so it just kind of stops moving, and it reaches the point that is as close as possible to our target while not getting the system unstable. All right. With that, I'd like to thank you for listening and my PhD student for doing all the work that I presented. Everything, like I said, is on a TAC paper that's been submitted, but if you're interested, you can go on the archive and take a look. All right, thank you.
So, questions?
It was so clear.
So you have always assumed that you have kind of do you need a perfect model of your system? How can you cope with modeling uncertainties there? any issue regarding that? And is there a difference between barrier functions and ERG in that respect?
I don't think there are issues between barrier functions and ERG in that respect. So how we handle these uncertainties on the ERG side is we can overestimate this Lyapunov level set. You say, okay, well, my system has a certain number of parameters, well, has parameters that are unknown, but those parameters are in this range. And so then you can basically provide a Lyapunov function that is, you take the worst case Lyapunov function and the worst case threshold value for the two, and then the ERG works. The CBF can use that same intuition, although I do think that it needs to be reformulated a little bit to sort of allow for the fact that at a certain point it would become infeasible. And then we can sort of go back to our pre-stabilizing control, which would be guaranteed to work. So the current theory doesn't support uncertainties on the CBF side. On the ERG side, it does, and I don't think that the step from one to the other would be that hard.
Okay, yeah. Thank you.
Thanks. So this is very interesting, although it's quite far from my own research area. It's very much in machine learning, and so so my question is also has to do with a bit of the relation between these fields. So in particular, all of your examples involve closed form expressions for the safety constraints that you want enforcing. But some of the applications, some of the control problems that you mentioned at the very beginning, you had sort of this very broad slide with autonomous vehicles, etc., will presumably also involve situations where the safety constraints are not captured by a closed form, but are rather data-driven in some.
You'd be surprised how well we know models of cars.
Okay.
So there's MPC that is model-based that knows the car dynamics as well as needed to get an MPC to run. And it does use invariant sets as well. And so those invariant sets have been validated. So I would say for mechanical systems, we've studied mechanics long enough that we have good models, good invariant sets, and we can do that. Now, there are other areas where that question is perfectly valid. For example, biomedical systems or systems that we don't necessarily know everything, or the parameter uncertainty is so large that we might want to learn some things. The answer there is that there is work on learning invariant sets for all these kinds of systems. With varying levels of success. And the methods tend to scale a bit poorly with dimensions of the system. But what I've seen is that the idea of defining a control law for your system and then learning the invariant set is still a better idea than trying to learn invariant set for a non-pre-stabilized system. So this whole starting idea of let's pre-stabilize the system and then design an invariant set on that, I think still carries over.
All right. Yeah, so you did, I think you guessed my question correctly. So I was indeed interested in sort of like how much of the framework like the one you're sketching now would carry over if that closed form assumption is violated. And I take it from your answer that the answer is partly.
But this is obviously a very interesting direction, and there are groups working on it. So yeah, there's a lot to be worked in that area.
Thanks. Great.
Thanks for the presentation. It was very nice. But even my question is, even in terms of cars, friction can vary according to conditions, right?
Yes.
So there can be some uncertainty there.
Mhm.
And is it hard to calculate or to find these Lyapunov functions for arbitrarily complex systems, or you will always find them?
No, you don't always find Lyapunov functions, but it is much easier to find a Lyapunov function than it is to find a control barrier function, due to the fact that we've been doing research on Lyapunov functions since 1970, and we've been doing research on control barrier functions since 2020. So the ability to take the literature of how you design Lyapunov functions and say, here, take it, and here's a control barrier function that works, that's what's appealing to me.
Thanks.
Are there other questions?
Thanks, Marco, for a nice presentation. Elaborating on one of the previous questions, let's imagine that there is a change on the tuning of the controller. So, how do you foresee the actions of the control boundary in that case? Because it can be not feasible. So
Sorry.
how would you do it? And my second question is, how would you sell this into a factory? Imagine a chemical plant, or as you said, a macro grid, in which you have many devices and you have local controllers. You said, or you stated at the beginning, that it's easier to implement a posteriori action than a priori action, but that means cutting a lot of wires, planning again the whole factory. So in which kind of applications you foresee this kind of a posteriori control actions?
So I'll answer the second question first, and I'll have to ask you to rephrase the first. What kind of places would we see kind of the preference of putting safety filters as opposed to tearing down the control law and replacing with an existing one? And the answer to that is any industry that is risk adverse. So aerospace industry, chemical plants, things where you've had to go through a very complex ether to get to a control law that you know you've validated and it works, and they don't necessarily see the advantage of going through a whole new redesign that might take years, when they can just take something off the box and filter an existing thing. This is, I'd say, the main pitch for reference governors is that, oh no, you're not changing your controller, you're just putting a filter on the reference. CBFs would be a similar discussion. It's like, well, you're not changing the controller, you're just putting a filter on after it. But yeah, I would say the main industries that are interested in this are the risk-adverse ones, whereas the ones that are going to try to push for performance as much as possible and are more open to risk would go towards a more model predictive control approach. And then could you repeat your first question?
The first one, was related to the tuning of the pre-compensated system.
Yes.
As one of the previous questions formulated, what happens if the controller, let's assume a PID, a simple PID, is untuned, how the actions of the control boundary functions will be in that case, because it becomes not feasible, no? You cannot design a Lyapunov level set for all the possibilities that you have with that controller, or you will do it.
I don't need to design it for all the possibilities. I need to just have one Lyapunov. Are you saying multiple? Oh, well.
Multiple tuning parameters. So
That would be the same thing that I guess I answered to Michelle. This particular framework, which is new, wouldn't handle it, but you can sort of consider robust invariant level sets. You can consider external disturbances if you have input to state stable Lyapunov functions as opposed to normal Lyapunov functions. And then, yes, parameter uncertainty, you would sort of need to do something like worst case scenario and go with that.
Okay, so I will keep my privilege as chair of the session to make the last question.
Okay.
Actually, I have a comment about calling this a filter, because it's not a filter. Actually, it might increase the bandwidth of your system because it has nothing to do about retaining the frequential properties of the original controller.
You are correct. That's
But I mean, it's I would say marketing, but not saying the truth.
I agree. I didn't come up with the term. I just use it. But yes, I agree. It does increase the bandwidth of the control input.
In other sense, it's not true that it's something that is on top of an existing control loop. It's a different control law to cure that might be based on a control law you have, but if for whatever reason you're not exciting certain modes, now you could excite them.
Yeah.
Okay, so after this question, of course, to make you uncomfortable, are you happy?
Yeah, well, did I get my PhD?
Too late, unfortunately. So after that, we can close here for this first part of our seminars at BrIAS. We can have, as usual, our coffee break, and we will be back soon.